Hi class, my name's Ari and I'm going to try and teach you all about maps, graphs, and circuits. This is chapter 6, section 3 from the textbook, and I decided to title it "An Election Isn't the Only Reason That Maps Get Colored." I wanted to throw in a little quote from our textbook because I think it's something important to stop and think about. You may not think that using simple math to solve a real-world problem would be beneficial, but after this chapter you might start to think differently. I would now like to introduce a few terms before we get into the confusing stuff of this chapter. A planar graph is a graph that can be drawn on a plane and not have any sort of crossings within it. The only crossings that are technically allowed would be at the vertices. We should all also be familiar with Euler's characteristic. This is from chapter 6, section 1. This utilizes V minus E plus F. In some cases, it can be R for regions. And lastly, mathematical induction. This is the idea that we can prove anything with a consistent argument in the terms of graphs. K sub 5 and K sub 33 are examples of graphs that would not be considered planar. I'll be showing an example of both a planar and non-planar graph shortly. Essentially, the 5 and the 33 represent the number of the vertices. A sub 5 graph has 5 vertices and 10 edges. Because of this, there's no way to connect all 10 of those edges to the vertices without creating unnecessary crossings within it. This goes the same for sub 33. Moving right along, these are examples of planar and non-planar graphs. You can see how intricate the planar graphs have to get in order to avoid any sort of crossing. This is where things might start to get a little bit confusing. The four-color theorem, being the more complicated of the two that we're going to discuss, was first discovered by Francis Guthrie in 1852. He failed to prove his point, so over 100 years later, in 1976, two mathematicians by the names of Kenneth Appel and Wolfgang Haken took true credit for finally proving that this theorem was possible. The six-color theorem, on the other hand, was a lot easier to prove for mathematicians. This is obviously because they were able to use more colors, making it a lot easier to have the colors not sharing the same regions, at least no more than two. These are examples of bad coloring and good coloring in the terms of using the four-color theorem. As you can see on the left side, there's two regions within that graph that share yellow. That wouldn't be allowed in the case of the six-color theorem, and later on it took them way too many years to prove that it is possible with the four colors, as you can see on the graph on the right. Moving on to some problems for this chapter. The first one should be pretty easy. We're going to be utilizing Euler's characteristic theorem, V minus E plus F, or in some cases R, for regions, as I mentioned previously. The second problem is describing the six-color theorem, which is easier than the four-color theorem, and you need to point out what is unique about the four-color theorem. I'll give you a few seconds now to think about these. The answers are coming up next. If you said that this graph was satisfied by Euler's characteristic, you would be correct. There are 7 vertices, 9 edges, and 4 regions. That ends up coming out to 2. The four-color theorem took forever to be proven, and the six-color theorem took no time at all. The six-color theorem is truly guaranteed to work with any and all maps. We can't really say the same for the four-color theorem, as we saw in the previous example. I'm going to wrap things up now, so here are a few things to remember from this chapter. I want you to think about what else in this world is undiscovered by mathematicians, both in the real world and in the math world itself. Thinking back to that quote from the beginning, it really makes you think about how many more things there are to come.